Hello everyone, welcome back to this NPTEL lecture series on cycloaddition. So far we have already completed 4+2, 3+2 and 2+2 cycloaddition reactions. What we have not done so far is the mechanistic approaches which will actually predict whether these cycloaddition reactions are thermally allowed or photochemically allowed. So that is what we will discuss today. As you know, there are three major mechanistic approaches which are used to predict and analyze whether the particular cycloaddition reaction will be thermally allowed or photochemically allowed. The first one, which is the easiest one, is Zimmerman-Dewar approach. Zimmerman and Dewar, they independently developed transition structure aromaticity approach. So, which was the quite simple method to predict whether particular cycloaddition reaction is thermally or photochemically allowed. In early 60s, Woodward requested Hoffmann to come up with theory about the ideas which he had about predicting all the pericyclic reactions, whether they are thermally or photochemically allowed. So, that became a well known and world famous Woodward-Hoffmann rules. Later they continued their studies and they developed this orbital symmetry correlation, which is nothing but conservation of orbital symmetry from the starting material to the product. First, let us start with the Zimmerman-Dewar approach, and before actually we go into Zimmerman-Dewar approach. So, when you see any Diels-Hall reaction or dipolar cycloaddition or 2+2 cycloaddition, you will always see S and A. So, we call it as supra and antra. So, what is this supra and antra? Supra means it is supraficial, antra means it is antraficial. So, what does it mean? So, whenever a new bond is developed, and if the new bonds are developed from the same phase of the pi component, then it is called suprafacial. Okay, for example, here you can see the new bond is being formed from the same phase. Likewise, you can see here again it is from the same phase, and if you take butadiene molecular orbital, again you can see the new bonds are formed from the same phase of the pi component. So, then this is called supra, and sometimes these new bonds can be formed from the opposite phases of the pi component, then they are called antrafacial. For example, the same molecular orbital, the pi component molecular orbital, now the bonds are formed from the opposite phase. Likewise, you can see for 4 pi electrons, the bonds are formed from the opposite phase. So, these are called antrafacial connection. Okay, in short, they write S and A. So, now let us take Diels-Hall reaction, how this supra and antra you can use it in Diels-Hall reaction. So, when you look at Diels-Hall reaction, basically it is a 4 pi electrons and then 2 pi electrons coming together to form a 6-membered ring. So, stereochemically there are 4 possibilities. One, you can see this is the 4 pi component, this is a 2 pi component. In the 4 pi component, again you see the new bond is formed from the same phase, and here the new bond is formed from the same phase. That means it is pi 4s and pi 2s. And in this particular case, you can see here it is from the same phase. That means it is pi 4s, whereas in the case of 2 pi electrons, here it is from the opposite phase. So, that means it is pi 2 antra, okay, pi 4s and pi 2 antra. Then it can be reverse or opposite. The Andra can be at 4 pi electrons or supra can be in 2 pi electrons. So, that is what happens, you can see. So, this is Andra and this is supra. Okay. So, it is phi 4a plus pi 2s. Then the last possibility, the fourth possibility is both are Andra. So, you can see here these two are from opposite and here also opposite phase. So, that way it is pi 4a plus pi 2a. So, among these four, for any pericyclic reaction, one particular mode will be highly favorable, and that will determine whether that reaction will go under that condition. And sometimes it may be symmetry allowed, but geometrically not possible. Okay. This also will happen in some pericyclic reactions, which we will discuss sometime later. Now, we will go to transition structure aromaticity approach. So, this is actually based on either aromaticity or anti-aromaticity of the pericyclic transient state. Okay, this approach is based on aromaticity or anti-aromaticity of the pericyclic transient state. So, Dewar used the PMO theory, that is perturbational molecular orbital theory, for aromaticity and anti-aromaticity in cyclic conjugate system. And normally when you talk about cyclic conjugate system, you use either Huckel or Mobius. Mobius means it is opposite to Huckel, so we call it as anti-Huckel. Zimmerman used the Huckel or Mobius system based on the Huckel molecular orbital method. So, both are almost same. So, that is why end point is, according to this approach, a thermal pericyclic reaction, whether it is electrocyclic or cycloaddition, a thermal pericyclic reaction normally proceeds via aromatic transient state. Okay. A thermal pericyclic reaction proceeds via aromatic transient state, while a photochemical reaction proceeds via anti-aromatic transient state. Okay. These two are very important. Okay. Then how do you know which is aromatic and which is anti-aromatic? Because the transient state, you should know this particular transient state is aromatic and the other transient state is anti-aromatic. So, what are the steps involved to identify that this particular transient state is aromatic and the other one is anti-aromatic? So, what you do, first you take the basis set of orbitals, okay. Only the base one. For example, butadiene, you should take psi 1, and for ethylene you take only pi. Okay. So, this is how you take the base orbital for each reacting component of the pericyclic reaction, in this case cycloaddition. Okay. So, now then you draw the ring or the cycle and assign them as Huckel or Mobius based on the number of sign inversions, okay, based on the number of sign inversions in the cycle. In the ring which you form, you have to see if there is any sign inversion, and accordingly you can call them as either Huckel or Mobius system. So, how do you do? If there are no sign inversion or if there are even sign inversion, then such systems are called Huckel systems. And if there are odd number of sign inversions, then they are called Mobius systems. Okay. So, this you should remember, it depends on the number of sign inversion. If it is odd, it is called Mobius. If it is 0 or even, it is called Huckel system. Okay. The third step is, now based on this number of sign, then you should assign whether it is aromatic or anti-aromatic. Okay. There are two pi components which react and then you get a ring. If the two reacting components have together 4n plus 2 pi electrons, then this is called aromatic, and it is a Huckel system. And Mobius system, it is anti-aromatic, If it is 4n pi electrons, it is anti-aromatic under Huckel system and aromatic under Mobius system. So, what does it infer is any aromatic system, okay, is thermally allowed, whereas anti-aromatic is photochemically allowed. So, this is what you should know. That means 4n plus 2 Huckel system is thermally allowed. 4n Mobius aromatic thermally allowed, and 4n plus 2 Mobius anti-aromatic photochemically allowed. 4n Huckel anti-aromatic photochemically allowed. Okay. Let us take 3 examples, then you will know how easy it is to assign whether the particular reaction is thermally allowed or photochemically allowed. Let us start with our 4 plus 2 cycloaddition reaction, where you have 4 pi electrons and 2 pi electrons. So, this is how first you draw the base orbital, and now if you connect it to form the ring through these dotted lines, when you see the dotted lines, you cannot see any sign inversion. There is no sign inversion. You can see here it goes like this, and there is no sign inversion. So, that means the number of sign inversion is equal to 0, and obviously it is Huckel system. 0 or even number of sign inversion is Huckel system. So, if it is Huckel system, then you should look at how many pi electrons are involved in the ring formation. So, here it is 4 pi plus 2 pi. So, overall 6 electrons are involved. So, that means aromatic. Huckel system aromatic, that means this is thermally allowed. Okay, very easy. Now, let us look at 2 plus 2. Again, you take the base orbital and then connect this ring. So, when you do that, again you see there are no sign inversion, 0 sign inversion. That means it is again Huckel system. The next step is how many pi electrons are involved. Here only 2 plus 2, that is 4 pi electrons are involved in the formation of a member ring. That means it is anti-aromatic. So, Huckel anti-aromatic, so that means this is photochemically allowed. Again we will go to 2 plus 2, but this time it is not pi 2s plus pi 2s, it is pi 2s plus pi 2a. So, this is already we discussed, if you recall, the thermal 2 plus 2 cycloaddition that goes through this type of transition state. Here particularly you see this sign inversion. Okay. When you draw the 4 member ring, in one particular place you see the sign inversion. That tells this particular transition state has one sign inversion. If there is one or any odd sign inversion, then this is called Mobius system. What is the next step? You have to calculate the number of electrons. There are 4 pi electrons involved in this, and it is aromatic. Mobius system, 4 pi electrons is aromatic. So, what do you infer? It is thermally allowed. Okay. So, this is a very simple approach to predict whether any particular pericyclic reaction is thermally allowed or photochemically allowed. Now, let us move to the Woodward-Hoffmann rules. So, Woodward and Hoffmann in early 60s, they predicted certain rules, and these rules are very helpful in determining or predicting whether the particular pericyclic reaction is thermally or photochemically allowed. So, for a thermal reaction to happen, so normally you look at the ground state process. Okay. And a thermal pericyclic reaction is symmetry allowed when the total number of 4q plus 2 s and 4ra components is odd in number. So, what is q? what is R. And as you know, S means suprafacial and A means antrafacial. And Q and R, they are simple integers. It can be 0, it can go all the way to any number. Okay. So 4Q plus 2. Okay. When you talk about 4Q plus 2, suppose if it is 0, that means 4 into 0, 0 plus 2, that is 2. That represents 2 pi system. And Q is 1, then 4 into 1, that is 4, 4 plus 2 is 6, that represents 6 pi system. And if it is 2, if Q is 2, then 4 into 2 is 8 plus 2, it is 10. It represents 10 pi system. And if R is 1, then 4 into 1, it is 4, it represents 4 pi. Likewise, if it is 2, it represents 8 pi system. So basically, from this what you infer is the dienes normally one can represent in the form of 4R system. You know, when you talk about dienes, it is 4 pi electrons, 8 pi electrons and so on. So in short, 4R can be well represented for dienes, and for dienophile you can use 4Q plus 2. Normally dienophile has 2 electrons. Okay. So 4R mostly for diene and 4Q plus 2 for dienophile. Okay. And for the photochemical reaction, as you know, it is a symmetry allowed when this 4Q plus 2 plus 4RA is 0 or even. So these are the two rules which Hoffmann and Woodward proposed in early 60s. Okay. What is important is for thermal reaction happen, this together should be odd, and for photochemical reaction to happen, these two together should be either 0 or even. Let us take the 4 pi electrons, pi 2s plus pi 2s, 2 plus 2 cycloaddition reaction. Now in this case, both are pi 2s. Okay, you can see symmetrical. Okay. So then how many 4Q plus 2 are there? Okay. So 4 into 0 plus 2 is 2. So there is 1 2 and there is one more 2, 2 plus 2. So that means you have 4Q plus 2s is equal to 1 plus 1 2, and there are no antrafacial bonds. So that means that is 4RA is equal to 0. So now if you add these two, it is 2, that means even. So if the total is even, then this reaction is photochemically allowed. Likewise, you can extend the same for pi 2s and pi 2a. Now if you see this, this is pi 2s, this is pi 2a. So though it is antrafacial, so 4RA is 0. Okay, you need 4 pi electrons. Here there are no 4 pi electrons, so this is 0. But we have pi 2s, that is 4 into 0 plus 2. So that means you have 2 pi electrons. So that is here only 1, 2 pi electrons. So it's here. The total number is 1, which is odd. That means this reaction is thermally allowed. But you know, from the geometry point of view, this reaction may be very difficult. Okay. So now let us move to 4 and pi plus 2 pi electron system. Here you have pi 4s, 4 pi electrons, and you have 2 pi electrons. Both are suprafacial. Okay. So that means you have to look at the 4R. 4R is 0. Why 0? There is no antrafacial. Though you have 4 pi electrons, but they are suprafacial. So there is no artificial component. So, 4R is equal to 0, and then 4Q as usual is 0 plus 2, that is 2, you have 1 2 pi electrons. That means the 4Q plus 2 in this system is 1, and already as I said, there is no artificial component. So, that means it is 0. So, together the total is 1, that means it is odd. So, this is thermally allowed. Okay. So, just you should remember 4Q plus 2 and 4R, and 4R means it is exclusively antifacial, 4Q plus 2 means it is suprafacial. Okay. So, many times you do not get the antifacial. So, that is why you have to be specific with 4Q plus 2. So, now we will move to the most important topic of mechanistic approach to predict whether the cycloaddition reaction is thermally allowed or photochemically allowed, which is called orbital correlation diagram. So, the orbital correlation diagram comes from the fact that there should be conservation of orbital symmetry when a particular reaction goes from starting material to product. So, what happens when you carry out pericyclic reaction? So, during the pericyclic reaction, the orbitals of the starting material are smoothly converted into orbitals of the product. Basically, this is what happens. Okay. So, what do you get? What information you get from this? The information which you get from this is the symmetry of the orbitals with respect to any symmetry operation must be conserved while moving from starting materials to product. This is very important. Okay. So, this is called conservation of orbital symmetry, and this is what you will see in the orbital correlation diagram. First, let us start with the orbital correlation diagram for 4 plus 2 cycloaddition. So, before actually we discuss about orbital correlation diagram for 4 plus 2 as well as 2 plus 2 cycloaddition. So, what is important is you should assume that you can have any substituents attached to diene and dienophile. Okay. It may increase electron density or it may decrease electron density, does not matter. You just do not have to include the effect of any substituents. You are going to talk about the orbitals, that is all. Substituents you do not have to worry. Then how to draw? The first thing is you have to take the very basic bare bone of the reaction, okay, and write the curly arrows and identify the orbitals which are undergoing changes to form the product. For example, this is 4 plus 2 cycloaddition. So, you see there is a diene and dienophile, and you can see the arrows, how the arrows move forward, and through a cyclic transition state you get this cyclohexene. Okay. So, now you have done the basic thing, how the reaction works. Okay. The next step what you should do is you have to look at the pi orbitals of the diene. One of the reacting component is diene. So, then the starting material what you have to look at is what are the reacting components. There are pi orbitals of diene and pi orbitals of dienophile. Diene, there are 4 orbitals, normally we write psi 1, psi 2, psi 3 and psi 4. For the dienophile you write pi and pi star. In the product you have only one pi bond, so that means pi and pi star, but you have 2 new sigma bonds. Okay. So, that means you have to write sigma 1 star, sigma 2 star. Once you identify this, the next step is during the course of the reaction, is there any symmetry element which is maintained throughout the course of the reaction. Okay. For example, if you look at this diene and dienophile, you can see a mirror plane which is maintained throughout the course of the reaction. Okay. So, here the symmetry element present in 4+2 cycloaddition is mirror plane, which is called in short M. Okay. Now, let us move to the next step. Now, what you should do? Okay, you identified there are 4 pi orbitals and 2 pi orbitals in the starting material. So, you draw the molecular orbitals of the reactants in the order of ascending energy from psi 1. Okay. Then when you arrange also, it should be one above other, and you do that for starting material on the left hand side and do the same for the product on the right hand side. Okay. You draw the molecular orbitals of both reactants and products in the order of ascending energy. For reactants, you write on the left hand side, and for product, you write on the right hand side. So, now you have for 4+2, you can identify on the left hand side 6 orbitals, and on the right hand side again you identify 6 orbitals. So, now each orbital you should identify with respect to the symmetry element. Here it is mirror plane. With respect to the mirror plane, whether they are symmetric or antisymmetric. Symmetric means you write S, antisymmetric means you write A. Now, once you have done this, you have to do the next step, that is you have to construct the orbital correlation diagram. That means you have to connect via line from the starting material to the product. How do you connect? You connect the orbital of the same symmetry of the starting material with the same symmetry of the product without violating non-crossing rule. Non-crossing rule means, suppose you have a starting material with symmetry element S, which is the lowest, and you also have in the product you have another orbital with S, which is also the lowest. The lowest one should be correlated with the lowest one, and you should not go to higher one. Okay. So, that is called non-crossing rule. Once you do that, then you will see the orbital of the starting material moves smoothly into the orbitals of the product, and that too in the ground state, not in the excited state. Then it is thermally allowed. First, let us start with 4+2 cycloaddition. Okay. As I said, first step is write the bare bones of the reaction and identify the orbital. So this is the 4+2 cycloaddition reaction, and again I have to reinstate. So, this is the mirror plane which is present in both starting materials as well as products. Okay. Next step is you have to arrange the molecular orbitals of the starting materials and product in the ascending energy. Okay. So, let us start. First, we will start with psi 1. Okay. When you start with psi 1, now can you see the mirror plane? Is it symmetric? Left hand side and right hand side, you can see there is a mirror image. So, that means the symmetry element present here is S. Next is the pi bond, the pi molecular orbital from the dienophile. Again you can see the mirror plane is present and symmetry element is mirror plane, and it is symmetric. Next one is psi 2 with one node. Okay. Here you will see the mirror plane is absent. Instead of mirror plane, it has a C2 axis of symmetry. So, that means it is antisymmetric with the symmetry element present. Here the symmetry element present is mirror plane and it is antisymmetric. The next one, again now it is psi 3. The psi 3 has 2 nodes, but here it has a mirror plane. So, that means it is symmetric with respect to the symmetry element, that is mirror plane present. Next is pi star, which has one node, there is no mirror plane. So, that means it is antisymmetric with respect to the mirror plane. The last is psi 4, again it is antisymmetric. So, this is all about molecular orbitals of the starting materials and whether they are symmetric or antisymmetric with the symmetry element present in the system. Now let us go to the product. The lowest in energy is sigma 1. Here you can see all these are having same phase. So that is the lowest in energy. Next is sigma 2. Here these two lobes have same phase, but these two have opposite lobe, but still they are sigma 1. Okay. So that is sigma 2, and in this case you can see the symmetry, that is the mirror plane is present. So this is symmetric with respect to mirror plane, whereas here there is no mirror plane. So that means it is anti-symmetric. Next, that is a cyclohexene pi bond. So you can see clearly there is a mirror plane. So that means it is symmetric with respect to the mirror plane. Next high in energy is the pi star. So there is no mirror plane. That means it is antisymmetric. Next, it is a sigma star. Here, so both are antibonding, but if you look at this, these two are of same phase. So that means this is slightly lower in energy than the sigma star 4, but there is a mirror plane. Okay, the mirror plane still exists. So that means it is symmetric. Next, now here also antibonding, here also antibonding, and you can see more nodes. So that is why it is antisymmetric. So this is the excited one, this is the ground one. Okay. Now we have to do the correlation. Okay. What you should do? We should connect the orbitals of the starting material with those closest in energy and of the same symmetry in the product. Okay. I will repeat. You have to connect the orbitals of the starting materials with those closest in energy and of the same symmetry in the product. So now you are having symmetric here, the lowest in energy, and the next lowest in energy on the product side is this. You have to connect. Okay. The next one, so pi, which is directly connected to this pi. Next, antisymmetric connected to antisymmetric. In the excited one, that is LUMO side, symmetric to symmetric, antisymmetric to antisymmetric, antisymmetric to antisymmetric. Now if you look at this carefully, you can see that the bonding orbitals in the dienophile and diene, they are correlated with the new bonding orbitals in the ground state itself. It did not cross the intersection. So that is why this is thermally allowed. If it crossed, then it is photochemically allowed, which you will see in 2+2 cycloaddition. So in 2+2, what you see is there are two mirror planes, one horizontal mirror plane, other one vertical mirror plane. You can see both in the starting materials as well as product. So what you should do now, you write the orbitals in ascending energy. So now you can see there are 2 pi electrons. So here with respect to the two planes, okay, the first one you can see this is S1, okay, you can see the mirror plane, and this is also the mirror plane. Both symmetry elements are present. So this is S1 and S2. Next, if you see this side, there is no mirror plane, whereas here you can see there is a mirror plane. So with respect to M1, this is antisymmetric. With respect to M2, it is symmetric. Next, we go to pi 3. So here what happens? The M1, you can see asymmetric. The mirror plane is there in M1, whereas M2 you cannot see. Okay, there is no mirror plane, the vertical one. So the first one is symmetric with respect to M1 and antisymmetric with respect to M2. The last one, if you see, with respect to M2, this is M1. Okay, with respect to M1, and M2 there is no symmetry, correct. And then we will go to sigma bond, that is in the product. Here you can see M1 and M2 both symmetry are present. Then you go to sigma 2, you can see here there is a mirror plane, so it is S1, but this mirror plane is absent, so it is A2. And here the sigma 3 star, again if you look at one sigma mirror plane is symmetric, the other one is not, so it is A1 S2, and last one is A1 A2, like here also it should be A1 and A2. So now you do the correlation. So what you should do, the S1 S2 is a correlation, and next one is A1 S2, but you do not have A1 S2 here, A1 S2 is here. So the correlation crosses this line, and the third one S1 A2, it also crosses the line. And the last one A1 A2 is directly correlating with A1 A2, which is the highest sigma star. So basically if you look at this, so now since it is crossing this, it is thermally not allowed, but even when it crosses within the first LUMO, this correlation takes place. So that is why this is photochemically allowed. Okay. So what we have discussed today is about 3 different mechanistic approaches which helps us in predicting whether the particular cycloaddition reaction is thermally or photochemically allowed. We will discuss in the next lecture the summary of all what we have discussed so far in this course. Okay. Thank you.